All right, the floor is yours.
Mm-hmm. Hi everyone, my name is Kirill Nekludov. I'm postdoc at Vector Institute for Artificial Intelligence, and today I'll tell you about our joint work with Rob, Daniel, and Ali, which we call action matching. And I would like to first talk a bit about the motivation of the work. And I think the motivation can be described by this slide, where we observe some process, like some distribution changing in time, and we are trying to inference the underlying process changing this distribution. And what's important here on this animation is that the samples which we have, they're uncorrelated in time. So we don't have like smooth trajectories, even like not smooth trajectories, stochastic trajectories. We don't have them at all. Instead, we have like what people call in trajectory inference, we have like population snapshots. Uh, and you can think about the following problems. That's, for example, the single population, it might be like a population of cells where every sample is like a latent representation of a cell. And you don't have trajectories because once you kind of measure the cell, or like once you take this latent representation of a cell, you destroy the cell. So you cannot trace a single cell in time. And the same happens in quantum mechanics, because like we can evolve some wave function in time according to like Hamiltonian, but once we measure it, we collapse the wave function. And once again, we don't have like notion of a trajectory. We cannot measure it like after the we cannot measure it once again and get its trajectory, right? So, and the last one is like from social sciences, you can think that you have some opinion of like people that you try to get um, using just by polling people. And of course you do it like independently. You just like let's say like once a month you um, you poll independently a number of people, and you don't track every single person individually. So you don't know how the opinion of a single person changes, but you know how they like the distribution changes, and you're trying to get the model how it changes, the distribution changes, like to predict, for example, or try to even like guess how like a single person opinion changes. Um, so the data we have in this problem might be represented like this, might be visualized like this, where we like on the animation, you clearly see that like the distribution, like something drifts to the right. And for every moment of time, we can uh, get number of samples. Here, time is represented with the color. And for every moment of time, we can get the number of samples uh, and just like store it as our data. And we will assume that we have like data very dense in time. So like for any moment of time, we can sample as many data as we wish. Okay. So this brings us to the problem statement, where we trying to recover the vector field driving the distribution. And now we are like going to the vector field. So I have to, yeah, so we have to discuss like more precise mathematical statements to try to solve this problem. Um, to discuss this, we first have to discuss the continuity equation. we have these initial samples, and they evolved according to this vector field, which are visualized with using these integral curves. And this is very simple. Like every sample just like flies along these integral curves. So we just solve these ODE, and they move like this. So we can see with our eyes, right, that like the density of sample changes. And that's what continuity equation tells us exactly. It tells us how the density changes. So Qt is the density of samples, which depends on time t. V of x is our vector field, so it's like an arrow at every point of the space x. And this operator is divergence, which is like sum of derivatives. So the continuity equation tells us if you give me the density and you give me the vector field, I'll tell you how the density changes in time, right? At every point. And what we are trying to do here, we are trying to solve kind of the opposite problem. We are trying to ask the continuity equation, okay, let's say I know how the density changes. Can I guess like what's the vector field uh, which does it? And we can think of that like we just like see this density that's like a Gaussian drifting to the right. And let's look at the like examples. So the examples might be like samples might be like drifting to the right and then like rotating around the center of the Gaussian on the way, for example. Another example is that they might be doing some like weird stochastic process on the way. So they just like drift and there is like some Brownian motion. And in general, we cannot do like there are like multiple vector fields that yield the same change of the distribution. So in a sense, it's like ill-posed problem still. So to make the problem well-posed, we say, okay, let's choose the vector field that does the minimal job. So here you see that we choose the vector field that uh, does the drift to the right, but don't include any rotation around the center of the Gaussian. We can formalize it like in the language of mathematics as follows. We can just say, okay, let's choose the vector fields on the right that like satisfy the continuity equation. That's like our strict condition. Restriction, right? And choose the vector field that minimizes this. And this is simply the kinetic energy, the average kinetic energy. So for every distribution Qt of x, we just take the expectation of the vector field squared. And then we like integrate it over time. So this is very simple. We can write down the Lagrangian of this problem. So this guy here is the Lagrange multiplier, even though like it's in continuous space, um, it serves the same purpose as in the like um, as a regular Lagrange multiplier, which might be like a vector or a scalar. And we take the functional derivative, and this will be just like v minus nabla s. And of course, for like optimal as an optimality condition, we have to say that this derivative has to be 0. So in the end, just v equals that nabla s. So we know that this vector field is a gradient flow, and this is also unique. So we can use it in our like to solve our problem. We now know about our vector field a lot, and we can go to the algorithm, which is the learning this vector field. Do you have any questions, guys? I feel like
I have
I
a
don't have
question. Yeah,
any feedback about how fast I go and how like how easy things I should discuss, how like simple things.
yeah, I have a question about the vector field that you just described. Is that
Mm-hmm.
then gonna model the sort of simplest version of this transition of the distribution? Like,
Model which version of the distribution?
so you showed us this Gaussian that evolves over
Yeah.
time, right, on a straight line,
Mm-hmm.
and then there is the rotating one, and then there is the one with the Brownian motion. So
Mm-hmm.
the vector field that you just described, then is it going to model
Mm-hmm.
only the box on the left here, or is it going to
Yes.
model the exact? So you can only model basically this simplest transition.
So okay, it doesn't it like so what I was trying to say before is that there is no notion of exact vector field,
Mm-hmm.
right?
Okay.
You don't really know what's happening because uh like this might be the ground truth like answer, right? This might be the exact one. Or I'm saying that like for every evolution of the distribution, we want to make like a correspondence. Density
Okay.
change corresponds to some vector field, and in general, we cannot really say which vector field does it, but we can say, okay, if we just restrict the family of vector fields to be kind of like curl free without all these rotations, then we will recover gradient flows. So like if we kind of like restrict our attentions to the vector fields with the minimal kinetic energy, or which will be also like equivalent to kind of to optimal transport family, and we'll recover these like gradient flows. That's what it does.
Okay. Thanks.
Hmm.
I have one question. So far, before you said that you have samples, but now it seems that you are assuming that you actually have access to the density in itself. Is it part actually of the assumptions, or you're going to reconnect the map then to the samples instead of the density? Because of course it's highly non-trivial to recover a density from the
Of
samples,
course,
right?
of course. Yeah, yeah. So right now I was just like describing the thing in like in a very like abstract way. Just not like we didn't get to the learning algorithm yet. I was about to get it at the next point on our list. So far we were just describing like things in like just abstractly, without, yeah, we will assume that like the density is not given on the samples. Sorry guys, like I'm having troubles with these like Microsoft Teams. How do I like I when I present I don't see you. So like how do I share my slide and I also can see you? Do you
No,
know?
you usually cannot. You usually need to have the chat on a different screen if you have it.
Oh, I see. Okay.
Yeah.
Okay, no worries. So
Yeah, that's annoying.
mm, yeah. Let's go to the algorithm. We discussed that, okay, now for the change of the density qt, which is, yeah, it's not necessarily density, right? It's just the change of density corresponding to some distribution. We might not know the density. We make a correspondence with some ground truth vector field nabla s star. So, and we want to learn this nabla s star, right? So let's try to
So
learn it.
maybe if I just for my clarity, uh, you actually assuming the existence of a density, or or the density could be singular, like delta distributions or manifold supported?
I assume that the distribution we observe has some density, but we don't have the model of this density, okay?
Okay, so it wouldn't necessarily work in a situation in which the distribution does not have a density.
Um, yes, I just like, yeah, there are definitely, I think, some examples like this, but I think it's very exotic, I would say, right?
I
Like
wouldn't say. I think in most real application, you're so close to actually not have a real density because the data is actually lower dimensional that you're basically in the singular domain.
Oh, I see. So like you mean like when we don't have the right like support of the distribution, like the dimension? Yeah, maybe that's true. But so here, I think to be precise, we operate in like it's called. I think it's better to refer to these like Wasserstein manifolds. So like basically, once you can pose like optimal transfer problems for your distributions, then you're pretty much like, so it requires, I think, finite seconds momentum, and uh, that's pretty much what you need, because you can write like many proofs without actually using the density. You can like use like generalized uh non-generalized, you can use the continuity equation in a weak form,
Yeah.
which doesn't require you like differentiation through the density, for example, right? And so on and so forth. Here I'm just like I'm showing like sketches of proofs and not going to like very rigorous details, but I'm pretty sure you can write the same thing like when your like dimensionality of your distribution is lower than the space you consider.
Thanks.
Mm-hmm. Okay, so let's we want to learn this like nabla S star. We want to approximate it, right? And we just parameterize some function S as a neural network. So the function S takes a vector and outputs a scalar. And then we take the gradient, and this parameterizes our vector field, nabla S star, which we're trying to approximate. Of course, we cannot minimize this objective as it is, right? Because we don't know nabla S star, we want to learn it. That's why we open the brackets. We notice that the last part doesn't matter because it doesn't depend. It doesn't matter for optimization, right? Because it doesn't depend on S. And the problem is in the second, in the middle term. And in the middle term, which still has nabla S star, we find that these guys, they kind of like, we take it from here. We just use continuity equation. We do integration by parts a couple times, and we end up with this equation, which is like this guy on the left is equivalent in terms of optimization to what's on the right. And what's on the right has these nice properties that like it doesn't require density, because every integral here with respect to dx I can write as an expectation with respect to the corresponding distribution. And the only thing we need is like samples from different times, like q0, q1, and for any time t, qt, right?
Mm.
And the parameterization of our function s. So we can just sample, we can plug these samples into our neural network, evaluate it, and we can estimate this function. So one learning iteration is very simple. We just get a bunch of samples at time 0, at time 1, and then we get like a bunch of samples. We collect them from different times where we sample time uniformly between 0 and 1. And we just plug all this into this loss. Here we have boundary terms and intermediate terms. So boundary terms correspond to these first two batches, and intermediate term corresponds to the third batch. We evaluate this loss and update the parameters of using our like favorite optimizer. we update the parameters of our model S of X and theta. Then we can sample easily as follows. We sample X0 from our data because we don't assume anywhere like that we have like some simple distribution which we can simply sample from, right? And we don't model these distributions, so we have to take our first sample from data, and then we can integrate it according to our ODE, and we can do it just simply by using the earlier method. I think you guys know all this, so I won't stop on this for a long time. So let's go to the example. Let's say we have these like marginals, and here I just put like marginals, like 6 marginals from different time points, but we assume that like marginals from any time point is given, right? And this is the data we observe. It's uncorrelated in time, just like scatter plots. And we then we train action matching, and then we can take these data on the left from the 0 time, and then we can, for every sample on this scatter plot, we solve the ODE, right? We integrate it according to the vector field that we've learned, and we evolve the distribution according to this, right? So like we propagate the samples in time, we get this marginal, this marginal, this, and this. So we perfectly recover the marginals. I think it's also a good point for the questions if you have any.
So you said, sorry. You said for any intermediate time, but of course there is a continuous infinity. So
oh, it's not like okay. So you should think that like in practice. So once again, like if we do, for example, this question is like about what we can do at time point 3, or like how do we estimate this integral over time, right? So if we do, for example, generative modeling, we can define, for example, if we define this sampling process ourselves, like in generative modeling, you can think that this is the process of destroying this like image with some noise, right? And there we, of course, we can sample at any time because like that's what we control, right? The process of sampling.
But in that case, we already have a vector field.
Which vector field?
You mentioned, I guess you mean diffusion models, right? In which we inject noise.
Yeah.
But in that case, you can just derive mathematically what the vector field is.
Not necessarily. It depends on your process. It's like if your process, for example, is like, let's say you have like a compression algorithm with like some continuous, like, or even with discrete, but then you can interpolate between them. And you use like, instead of Gaussian noise, you use like a JPEG, right? And then you control the amount of compression. Basically, even if it's discrete, you can like interpolate between some images or like something, and then you don't have the vector field, right? And in practice, of course, you can take just like densely in like, so for some experiments that I'll show later, I just took like 100 time points, and then I just sampled from these like snapshots, as we discussed before. So it's not, yeah, that we have like infinite data. Yeah, let's go to probably variations of action matching. we assume that the process is guided by the continuity equation, and we can actually like describe any evolution of distribution by the continuity equation if we don't know like the ground truth vector field. We but what if we have like some stochastic dynamics? So we know like from some like prior knowledge about the process that it is the Fokker-Planck equation with some stochastic part, right? Which and like sigma t is given to us, so the variance of the noise is given to us. Then we can also incorporate this into our model. We just take this noise, and the loss, which we had before, it changes. So instead of the loss like this, we have this additional term. So here it will appear, and yeah, so it's pretty straightforward. Just like once we integrate by parts, this guy will appear, and we'll just get this loss. Yeah, I want to say that like the marginals, the evolution of marginals won't change. So because the evolution of marginals is restricted by the data, right? The data tells us what are the right marginals. So what changes here is the evolution, like the trajectories, right? The evolution of every single sample, and you can see it here. So on the left, we integrate using these like ODE, and every sample, it just like goes deterministically from initial point to the last one. And here we integrate using SDE, right? And every sample like has like these like fluctuations around, but the marginals are the same. Another option that's like is important for some applications is the creation and destruction of like probability mass via these like growth rate. So what happens here is that now the mass can be destroyed according to this growth rate or created according to this growth rate, right? So we can actually recover this growth rate from data and get the optimal one, which will be like S star. Yeah, you can like really derive this. And the loss, once again, it changes very simply. So we have the loss like this, and then we get this additional part, additional term.
Yeah. So in this case, are you assuming that the distribution stops being normalized, or you're assuming that you keep renormalizing as the mass changes?
Yeah, so you can have like both, actually. I think you can derive both ways. Yeah.
And so probabilistically, you will interpret as the probability of finding a particle in a given location, given your ensemble.
Yes.
Are you aware of application of this in diffusion models? Because I did wonder if this could have been beneficial. And
to be honest, do you mean like for image generation?
For example, or other fields like for generation too.
So I know of the applications of this in single cell development, because there like we have like marginal snapshots. We want to recover the dynamics, and that's very important for us to like being able to model cell destruction or creation or like growth of some cells apparently. And there, yeah, like people try to incorporate this into dynamics. Actually, we have like recently we wrote a paper where we also like have results that unbalanced these like trajectories. They are they model the cell dynamics much better. So For image generation, I don't really know. So maybe let's discuss the like how do we generate data, because now beside the OD that we were integrating, we also have like some weights. So every sample now has a weight, and we integrate the OD for the weight along the trajectory as well, right? So GT is the growth rate, and log omega t is the weight. And regarding this to be beneficial to the, so this is like without, it's just diffusion here. But what might happen, like a completely different behavior of marginals might happen if we introduce these kind of like, if we allow our samples to teleport in space. And I think one can argue that this is like beneficial if we like generate images, and then we have like some importance, right, of like images, and we can like hope that will fit the end marginal better for some reason. I'm not sure why. And then we have like importance of our images, and we can kind of like sort with respect to these like importance weights and say, hey, maybe these images like are of better quality than others. But I don't actually, I know, like, I don't have strong intuition for this. I wouldn't say that it will work much better. I'm not sure. But yeah, so if our process, like natural process that we are trying to describe with our model, involves something like on the right, then yeah, then of course it's impossible to simulate it without this.
Yeah. So, and one thing, yeah, of course, I mean, you have a continuity equation, so you're assuming continuity. So since we talk about biology, what if you allow particles to actually split? Do you get a tractable equation?
Allow particles for what?
Imagine that you have particles that can split, that they can branch into particles. So there is kind of a probability of split.
Yeah. So this actually, like, this is the growth rate, right? So the particles, like, they grow like by splitting, and now we have like more particles. Yeah, that's what it takes into account.
Oh, I thought it was just a default birth rate, but actually the birth rate scales with amount of mass with amount of mass for a given state. So if you have more higher density in one state, that can either make the growth rate higher or lower.
Yeah.
Oh, okay,
So,
I get it. Yeah.
So like it depends on like on the density here, but yeah, like like ST that we recover might, like, it changes in time and space, so it can, like, through dependence in time, it also can like recover the, not like explicit, right? We don't get like a formula that tells us, oh, this depends on like density like this, but just like through time and like observed data, it can learn the model of like that, like in this region where the density is higher, it grows higher, for example. But the mathematical tool for this is this, yes.
So this could be quite interesting for images, right? Because you can imagine, for example, that you could want to have some sort of modulation for preserving diversity of, or you could want to branch images that are high quality and suppress. I think there are several things that could have.
Yeah, maybe. I don't really like I mean, like, I work with generative models for images, but I don't like work with the, I would say, like production models. So I don't really know what people like solve in these problems, because these are like a bit different community, right? Like I believe that like people at CVPR and ICCV, they have like they really like push the numbers for these like in a very like practical way. So it's better ask them. But yeah, maybe yeah, it might make sense in some situations. I'm not completely sure how, like if we want to branch images, because we can also like think that like this is just like can be modeled like via like stochastic thing, and we don't necessarily need like unnormalized distributions as well. But yeah, I think it might make sense.
No, I'm
Uh,
also not convinced that is useful. But I'm sorry, I'll let you go in a moment.
yeah, no. Yeah, I see your point definitely.
I feel that it is true that a lot of practical people have a very good way of pushing the numbers, but those people usually are not very familiar with this sort of math. So I think there is a bit of a gap between the theoretical people and the practical people in diffusion modeling. And in this sense, this is quite high potential because the practically
Maybe.
minded people could spend centuries there without having a solid theoretical understanding. You won't arrive to. And the other way around, you may have great theoretical ideas, but they will not arrive to good quality because you need to do engineering on the top.
Yeah. It's you usually have to know everything to get the result.
Yeah.
Yeah.
Well, I mean, you will be surprised that if the practical diffusion literature is very pragmatic and very empirical, that it really does not require much math at all. At least for being a good practitioner. Of course, the top people have both, but there are plenty of successful people that either have one or the other.
I see.
Anyway.
Yeah, perhaps. So yeah, let's go to some results. This is like a synthetic data, and here it's just to get an idea how the data looks like. So there are like some like branching happening, and yeah, the crucial one is that like the data is like represented with like it's scattered with different colors, and that's what we have, like the data from 5 time points, like, and then we recover the trajectories from the data, and we also like we take it like to a real world data, to like single cell RNA sequencing, and we show that like it works quite well compared to these like methods that people developed in biology or like in computational biology. And the same we can do like for like quantum mechanics. Here like it's also kind of like a toy experiment, where we take like a quantum system, 3-dimensional. It's just an excited state of a hydrogen atom, and we like have like 100 snapshots where we sample from these from the like density of the corresponding like wave, from the corresponding density of the wave function. And here you see the histograms of the samples. And now from these samples, we can learn our model of the vector field, and we can start from the very first snapshot of the data. So from the samples from the very first state, and we can like simulate the time evolution of the system, right? And that's what we'll have. So like you can like see visually that this is like pretty much the same thing happens here. As we discussed a bit already.
Could we talk a bit more for the quantum? Because that's quite interesting, right? In that case, the trajectories do not exist.
Yeah.
And of course, you are neglecting the phase information. So you give a partial description of the evolution of the quantum system.
Yeah.
So how do you interpret? What do you get from this kind of analysis, from this kind of inferred trajectories?
So you first of all, like you can think of it like now you have like a model on a computer of your quantum system that you observed in nature, and you can like basically you can like sample as many samples as you wish in the beginning and get like samples in the end, right? but in potentially you can recover actually the Hamiltonian of this system, because you can write there are like deterministic interpretations of quantum mechanics, which basically write the continuity equation for the probability mass, and this is called it's either called like Madelung transform or the Broglie-Bohm theory. So and they basically describe like quantum mechanics like Schrödinger equation. They just like do like polar parameterization of the wave function. They plug it into the Schrödinger equation, and they get two equations, one of which is the continuity equation, and another one is the equation which tells you how your density changes. This will be kind of like a Hamilton-Jacobi formulation of quantum mechanics. So using this and learning this vector field, you can actually recover the Hamiltonian of your system. And one of the applications which I might think about is that's like you have like a quantum system. You designed a quantum system. Let's say you designed the quantum computer, but like continuous state quantum computer, right? And then you want to kind of calibrate it. You want to see how well your how precisely you implemented it. So you have to like measure it like a lot of times and get the model of it, and then compare it to your blueprint, right? And you can do this by recovering the Hamiltonian from observations and comparing to the Hamiltonian you've tried to design.
Thanks.
Mm-hmm. So we've already discussed a bit generative modeling, and this is this is not even like diffusion, right? Because this is just like linear interpolation in terms of samples. I don't think you can like I have tried, and I don't think you can formulate it as a diffusion. Yeah. So
because you don't have the square roots?
No. Yeah, maybe, but I think
because
that like
the regular diffusion is the Gaussian diffusion. The variance preserving one is the square root of 1 minus t plus, and then you have the square root of t, and then of course it's always the Uhlenbeck diffusion.
Yeah, I guess so. But I think the forbearance preserving diffusion, the formulas are a bit more complicated, because here I'm writing the like sampling process for this one, because I think there you have to like actually integrate some SDEs to get the conditional distribution, and you'll have some like exponents of something like to something, right?
Yeah, but it replaces t, so at the end you get the only real difference is the square root. Eventually, you will get another coefficient, which I call theta, but it's not universal in the literature. But you get something very similar to what you have. It's just that you have square roots there. I am pretty sure you can formulate an SDE that also give you that, but I don't have it from the top of my head. Well, I'm pretty sure, because for any given sequence of marginals, you can easily formulate an SDE that give you. You can simply backtrack the drift from a Fokker-Planck or from a reverse Kolmogorov equation. But I don't know how pretty it is.
Yeah,
it's a very ill-posed situations, right? Because you're just trying to recover the marginal. So there are infinite, as you were saying before, for the probabilistic flow, there are infinitely many SD that can give you the same marginals.
Yeah, exactly. So,
may I ask one question?
Yeah, of course.
Yeah, in this case, maybe I missed it, but how did you define X1?
X1, oh yeah, X1 is the data. Thank you so much. Yeah, I should have put it on the slide.
All right, yeah, thanks.
Yeah, I think you should be able to write an SDE for this. I think it's just not that like straightforward. Maybe with some time reparameterization, as you've said, maybe it will be easier. But okay, what I was like, it's just an example of a process for like for our purposes. Because another example is that like on the state space, you can take like you can do like super resolution. You can like just uh, destroy some of the pixels, right, and preserve the others, and you'll get these like super resolution. Here I actually destroy much more pixels. It's just for visualization purposes. I destroy not all of them. And you can do like you can now like also remove the color. You can say, okay, we start from a grayscale image, and then we interpolate between the grayscale image and the colored one. And if we know the vector field that goes from left to right, we kind of can learn the model that colors images, right? So here we have like some numbers, and if you take a look for like super resolution, for example, we like do great. So FID is here like 1.4. This is like for CFR10, and but for generation we do worse than like diffusion models, which is VPSD here, 3.7 compared to 10. However, if you look like so one might argue that like I think that's because of the nature of our like process. We get like we do less integration time steps like than diffusion model. Also, like if you look at the samples, it doesn't look like awful, because 10 FID might sound not good, but the samples are pretty like close. So the top row, the samples from diffusion model, the bottom row is like action matching. So maybe there is like some weird noise that's still like in the pictures, but in general it can generate quite good pictures. Yeah, so this is an example for colorization. So we start from the left one and we'll go to the right one, and that's all on the state space, right? So we don't do like conditional models. It's just the image like changes, okay? And another one, this is like super resolution. I like remove 3/4 of the 3/4 of the pixels, right? So like I have like I leave I every fourth pixel stays on the image, and then once again we do it on the state space. Right from these images, we define the process where we like interpolate to the full resolution image, right? And since we require only samples, we yeah, I think it's better to say once again. So since we require only samples, right? We don't need to model any like vector fields, or like we don't need to know anything about the process. So we can define any sampling process here. As I mentioned before, we can like do like image compression algorithms here, and so on and so forth. And yeah, we get these samples.
Can I ask a question?
Oh,
Yeah, of course.
On the two slides before, I don't understand how that is generative though, because you just the one before as well, because you said that X1 is the actual samples from the data set.
Yeah.
And so you cannot, like, I don't understand how you generate new samples then, if you don't have that X1.
So like you generate new samples as follows. You just like you start from what's on the left. So for example, if this is the sampling process for the data. So we use this process during learning. Once we learn the vector fields nabla s star, we start from the left. So here we start just from a sample from a Gaussian, right? And we integrate this sample like according to our vector field, and we get some image.
Okay. So the one on the right is actually the data creation, like how to create basically all the intermediate steps.
Yes.
And then you learn the vector field.
Exactly.
Okay,
This is the sampling process for the training, not for the test time, of course, because for the test time, yeah, maybe I'll go after to like these like histograms and show once again like what happens there. Yeah. Any more questions?
So I guess that this is essentially an iterative interpolation, right? But how did you define the discretization time, or what is the level of discretization over time from 0 to 1?
Sorry, I'm not sure I'm familiar with iterative interpolation.
So I guess that in order to generate a sample, I mean, you start with the one from the standard Gaussian.
Yes.
And then you get at any time t, right? You get like a noisy state of the noisy sample, and you iteratively update, or so basically you will do OD solver, things like that.
Exactly. So
yeah, right.
Yeah. But I don't think it's called like interpolation. It's just like we solve this OD. So once again, so this is our like data. Let's say it's not like images, it's just like scatter plots. And what we do is, so the sampling processes on this slide with images that I showed, the sampling processes correspond to the processes how to sample these scatter plots, okay? So once we have these scatter plots, we plug it in our training algorithm, and then we start from the very first marginal. So in our case, it's either pure like just like normal noise, or it is like image for like super resolution that we want to enhance, right? Where we have only 1/4 of like pixels and the rest is normal noise, or it is a grayscale image that we want to color. So we start with this. We start with this data for the test time. So what's on the bottom? It's the test time. And then we integrate our samples using these like ODEs. So how do we integrate it? We integrate it like this. We once again we start from some x0. We plug it into these vector fields, which is like nabla s, right? So we plug it in our network S. We take like autodiff, like we backprop with respect to the inputs. We get the vector field, and that's how we update our current image, right? So we added with some like DT to the previous. This is the easiest one, right? The simplest one integration method, but you can use like more sophisticated ones like dormant prints, like Rungikut, like the, which is I think
the milestone. Yeah, but I guess that the XT you get it from the interpolation, right? The XT that you have here in the Euler, you get it from the interpolation that you mentioned before, right? Or not?
Oh no, on the time there is no interpolation happening. It's just
yeah, because I'm confused how you can, or what exactly do you use the interpolation when generating samples?
The interpolation is so like it's how the training data is generated. Okay.
So that's only for training, not for.
Yes. So like on training, we assume that we have like samples from different times, right? So like this Q0, Q1, and for any T, we have samples from QT, and that's how we generate the data during training.
Yeah. Okay.
Could you stay on the loss on a moment? Because your model is extremely similar to the diffusion model. So I wonder, what is the actual difference if you use the same forward model in the loss? Assuming that you use the very same forward model, so which would be actually very similar to your first one. Could I see the loss? Can I see if I... Will it be the exact same?
Oh, you mean like you mean if we parameterize the vector field instead of a gradient vector field?
Yeah, exactly. Of course, you are parameterizing the function s,
No,
right?
it won't be the same. It is different. It is different. So first of all, you kind of just like plug in. So nabla s, you have it only here, which is the vector field, right? But ds dt s, you don't have it like, and you can't actually. You can parameterize the vector field. I mean, at least in a straightforward way. Maybe there is like some smart way, right?
But there has to be a connection. So one thing you don't have in a diffusion model is the final boundary term, but probably that's irrelevant.
No. But this term, so you have to understand.
Yeah,
that
I understand.
S
Yeah.
outputs a scalar, right?
I know that your S, but you could parameterize a diffusion model that way. You can parameterize the diffusion model in a way that it output a potential function, which, and then you can use the same loss. And I wonder if you would, but it's true that I don't think you will get the derivative in time, because you will get the derivative in space. So your nabla S will be very similar, but I don't think you will get the derivative in time. So that's the main difference. But there have been people parameterizing diffusion models using a scalar function and taking the gradient. It's not very popular at the moment in diffusion modeling, but people are believing that. Actually, it's interesting because if the forward pass is conservative, if the forward process is conservative, you're actually mathematically guaranteed that the backward process is conservative as well, so that the reverse process is conservative as well. So actually, you're not making any approximation in that case if you parameterize it through a scalar function.
Yeah, but what I found in practice that like usually the parameterization via vector fields, because I was like playing around with like parameterizing diffusion, like mostly rectified flows or like flow matching. So these guys, if you parameterize there with the vector field, or you can like plug in there like either a vector field model or like gradient flow model, vector field model usually works better. So I think it is in a way like, yeah, so mathematically you're like more precise. You kind of like put the right inductive bias, right? But apparently it doesn't work. Like it works worse. At least I think that's because we don't really know how to parameterize them properly, the gradient flows. So what I do, I take just like UNet and make a like a scalar output out of it. Maybe there should be like a better way to do it, like more smart. And like I haven't studied it like enough, I would say, to give an answer.
Can I ask another question? Maybe?
Yeah,
in the previous slide, because so the loss function is basically, it's kind of looks essentially like implicit score match, from the paper of Hyveran. But besides, with the only difference that the boundary terms are not present. I don't know if you have any comments about that.
So yeah, besides the difference in the boundary terms, it also doesn't have anything about the time derivative, right? And the reason is that the original score matching, which you refer to as implicit score matching, it solves a different problem.
It's not time dependent. It is not time dependent, right? Yeah.
Exactly. Yeah, exactly. So like it solves a different problem because like it just considers like a distribution, and it learns a score, the score of like nabla logarithm density of a given distribution, completely static. Here we instead learn the model. So we learn this part, right? So this guy here, we learn nabla F star. We say that essentially our problem formulation is dynamical. The density changes in time somehow, and we learn only the vector field, right? And if you even like go even backward, so here we have this, we learn this drift, right? So we learn the drift to the right. But imagine that your distribution is like super complicated. This is like a distribution of images, but you add like the drift to the images. You do like a very stupid thing. Like you add just like to every coordinate, you add some constant value on every iteration, right? So then the model of the drift is insanely easy, right? Because like it's just shifting the distribution, and you can learn it without knowing anything about the distribution itself, because the distribution itself might be very complicated. And yeah, this is a difference between score matching and action matching.
Yeah, thanks.
So it kind of look me that if you take a diffusion model and you take the limit of very small time interval between, then you will get to the temporal derivative term, because in a diffusion model you sample the noiseless image and the noise image, but of course you could sample a noise image and a bit less noise image, and you can split loss that way. And I wonder if the time derivative will result by taking the limit of keeping smaller the difference between the two.
Yeah, I don't think so, because yeah, I don't like, maybe you can get like some variations, but in general I don't think so, because in general they learned like different vector fields. So in general, like in diffusion models, you learn the score, and the score nabla log density is essentially a property of distribution at any point. And once again, in the example that I gave before, you can think that like your distribution is very complicated. For example, it's a distribution of images, but your evolution is very simple. It's just a shift along some axis, right? And once you learn the score, you learn the score of the distribution. So you learn the score of the images. But if you learn this, if you learn like action function, then you'll learn the model of the evolution, which will be like very easy, like very simple. It will be just like the shift according to some, but you don't learn anything about the distribution.
Okay, but when you learn the score is independent from the normalization factor, which removes the main computational complexity of the distribution. So in the score, I mean, I don't think you're right, because you're solving the same problem. In fact, you are trying to do the same generative modeling, and you get very similar performance. So it really cannot be that different. No, and of course, the score is not a vector field. Once you have the score, you can translate it into deterministic vector field. But did you actually try? Did you get? Did you actually compare it using the same forward process? Solve the two methods, get the deterministic vector field. Did you try to see? Are they very different?
They like it. Once again, I'm saying like, okay, in some cases it will be similar, and we can like see it like from here, for example, right? But what you want to like, what you have to know here, that like in VPSD you have the part that you don't train. The part of your like probability flow ODE is the part that is like it's fixed for the forward and the backward process, which you don't train. And in action matching, you don't have anything like this, right? So like,
no, you do. You showed that before. You have the forward process that you show in the previous slide.
No, I'm saying that like you don't have the deterministic part. Like if you are to compare these vector fields, right? So you don't, here you learn the score, and then you use this score in the Fokker-Planck equation to write the probability flow ODE. But here and there, like, you use the score and the deterministic part in the forward process, right? Here you just learn the vector field, and I can give you an example where they learn. I can give you like an example where they learn completely different things.
But what
Diffusion
you
model-
are you comparing the score and the vector field, or are you comparing the vector field obtained from the score and the vector field obtained from actual matching?
So if you compare in some cases you cannot compare the vector field obtained to the score. In some cases you can. If you have a diffusion process, if you have like a Fokker-Planck equation, then yes, you can compare them. They will be in some cases they will be the same. In some cases they will be different. It depends on your forward process, because your forward process can have a curl, but you can design a process where they are completely different. You just, like, once again, if you take a distribution of images and you add drifts according to just like shift in space, right? Then the score doesn't have anything in common with the evolution of the distribution, right?
There are situations in which the score is 0, but in general, you can. I mean, first of all, I do agree. Yeah, you have to, I'm of course assuming that there is no curl in the forward process. So otherwise, you can get whatever you want in the. Although again, it would. But if there is no curl, then everything is pretty much fixed. And then you're sure that there isn't a curl in the reverse process. You can prove it mathematically. So then it becomes quite similar what they will actually trying to get if you use the very same forward process.
Yeah, so if you use the forward process without the curl, and then I guess your probability flow ODE will be just like a gradient flow ODE, and then they'll recover the same, like this vector field will be the same as action matching vector field that it learns. But in general, you can, what I'm saying, like in general, you can design such a process where they are like completely different and there is no chance to match them.
Yeah, of course, because you're taking a choice. I mean, as far as I understand, right? But you're choosing choosing the generative process to be conservative, and then of course you can only match it if there isn't a curved term. But
no, it's not about it being conservative or not conservative. I just gave you like an example where like it's very simple. It's just like a drift, right? But I'm trying to highlight the difference. The difference is in the problem statement. One thing is to learn the nabla log density of the distribution. It's essentially static. It doesn't involve any. You can solve it for a single distribution. Like it doesn't change in time. And like once you learn nabla log density, you don't know how your distribution changes because you don't know how the density changes.
But that's not what the diffusion model does. The diffusion models are series of marginals, exactly like your model. Your final goal is to model the final target log density, but that's not what you're actually doing in a diffusion model. Strictly speaking, you're getting all the log densities, and then usually you don't care about the previous one. But you want, what the diffusion model does is to model the path of marginals, exactly like your approach.
So I was answering the question, how is it different from score matching? And score matching, it solves the static problem. Then like if we have to like be precise here, then like people in diffusion models, they use score matching as a subroutine to get scores at any moment of time to write the probability flow OD, of course, yes. But like score matching is a static problem, and like having the scores nabla log density, there is no chance you have the evolution of the.
Yeah, of course. I'm sorry. I feel we're talking about slightly different things, because when I meant score matching, I meant kind of modern diffusion-based score matching, which is always time dependent in the sense that you're always doing some sort of time dependencies in the forward process, at least in the mainstream applications. But of course, the classical score matching paper are only trying to match the score of the target.
Yeah, so of course, like this conditional like score matching, you have the conditional distribution. Once again, it's not necessarily like time dependent and just the conditional, but then you use this like conditional score matching to do time dependence. Yes, and in that sense, like if once again, if your process is a diffusion, right? Because like sometimes you don't really know the conditional, it's hard to write it. Then of course it is very similar. I mean, we can clearly see it from this slide, from the pictures, right?
Yeah. Yeah, I just wonder if your loss, because I think we agree that if you use the same forward model, which is curl free, most likely the optimum is exactly the same in the sense of the vector field.
Yes, I guess so.
So, but we are using two different loss functions. So for me, it opened an interesting questions. One, how they connect, because they should have the same optimum, or at least it's my conjecture, but I feel that it's a safe one. And if they can kind of hybridize, because they're definitely, they're quite different in the way that I work. There are similarity, but they are quite different. You have the time derivative, but you don't have the conditional sampling. I do feel that the time derivative replaces the conditional sampling because it's like an infinitesimal conditional sampling, but that's just the feel I get from looking at it.
Maybe, yeah, maybe there are like some connections. Yeah. I think you can. So I'm not sure if you can prove that these objectives are the same, because so the difference here, if we talk about objectives, so this guy, it can be like 0, right? Because this like nabla S star is the ground truth vector fields, and if once you learn it, kind of like you have it like this guy to be like this guy equals 0, right? But this L2 objective in diffusion models, I'm not sure you can have it to equal 0, right? Because it's essentially like up to some level. So because you can have like I think you are trying to match at the same point of space. You're trying to match like different kind of vectors, and once you match the like once you get the minimum loss, it matches kind of the mean vector at this point, and it is the optimum. You use it for generation, that's perfect, but your objective is not the same because it's not 0. But I might be.
But I think it's a constant term, though. I don't think that it will change the. Yeah, I agree. You cannot, of course, put equal to 0, but I think it will add a constant shift.
Yeah, of course. So you can like once you decompose this loss into like one which is like which can be 0, and then another like loss term, then constant term, then I think yes, you can say that these objectives are like equal in a way. I think we actually like yeah, let me finish the presentation, and then I'll open the paper, and I'll open the paper and maybe I'll point to some occasions. So this is the optimization problem that we started from, that like we have to respect the continuity occasion, and we select the vector field with the minimal kinetic energy. And but this is very close to the dynamical optimal transport formulation. So like you can think that like this is the only difference, right? So like in the dynamical optimal transport, you also optimize with respect to this process Qt fixing the endpoint marginals, so q at time 0 and q at time 1, right? And one thing you can get from this is that if you, on top of action matching, you kind of get outer optimization with respect to this process, you'll converge to the optimal transport. So another thing you can get from this is that action matching actually corresponds to the infinitesimally close kind of like optimal transport. So let's say that the optimal transport between qt and qt plus delta t is this like t star map. So then you can take these limits and you'll get these vector fields. So essentially, like, you get closer and closer on your like process between two distributions, and the optimal transport will the vector field that you've learned looks closer to optimal transports vector fields. So at every point of time, you kind of do like a little like optimal transport between distribution, and you propagate your distribution like this. There is like a whole like mathematical framework called autocalculus, which describes like geometry on these like Wasserstein manifold, and this gives like a geometric interpretation to action matching. And the geometric interpretation is follows: like, on this manifold, you have like a curve changing, like just like curve, right? And action matching, actually, of course, it corresponds to some process on the state space or like the like distributions or samples. And once we have this curve, what action matching does is actually it recovers the so the cotangent vector. If it's not like very clear why is it like cotangent, then like it shouldn't be, because like it is clear from the framework. So it recovers this cotangent vector, which can, like, of course, like curve has like a tangent vector at any point, but then like we recover the cotangent, which corresponds to this vector field on the state space where the distribution go, where the every sample go. Yeah. So this framework, if you want to read something about it, it's called autocalculus, and there are like books, different. So I think it's better if you just want to learn about it, if you email me and I'll send you some references. Yeah. So the optimal path here is the straight line here on this manifold is just the optimal transport path. And then we can actually like go a bit further. We can like define some Lagrangians, and we can see this curve as like Lagrangian action minimization things and so on and so forth. But this is like in our like you can read it about it in our follow-up paper, yeah, which we put on archive recently, if you're interested as well. Yeah. So I think that's it's about the presentation. You can find much more things in the paper. The codes, the proofs. It's the proofs are not very like difficult. Like, don't be like afraid of some like equations. It's very straightforward. And yeah, I also have some like prepared some notebooks with examples where you can like run it on Google Colab and see how it works. You can play around with this code yourself as well. And let me go to this to the paper. So what I wanted to tell you is, so I think that's what might be interesting for you. Here we compare the action matching to flow matching, or like rectified flows algorithm, and you can like take the objective there and you can decompose it into things. So action matching minimizes kind of this part and not this part. If everything is like, once again, like if we just remove the question about being like conservative, like curl free out of the equation, okay? So in general, it's like this, and I think this objective is quite close to what a diffusion model do. Yeah. So in that sense, yes, it is might be very similar. Yeah.
Also, there is a single solution, right? I mean, again, I'm not. If you have a series of marginals, let's say respecting some basic properties of continuity, and you have a curl-free vector field, is there a single solution to this problem, or there is still some gauge?
No. It is a single solution. It is a single solution. It's just the like in practice. So like for example, you were saying that like yeah, we can write the analytic formula for the vector field for like diffusion models, and yeah, let me find this equation. And that's what actually flow matching does. So like this guy, for example, right? So Qi here is the density, like conditional density of normal distribution. And this is the vector field for these like linear interpolation process, like actually for any process. I parameterize here like sigma t ft. So you can write this equation, of course, but this is not like curl free, even when like f is curl free. So that's very that's kind of delicate. Yeah. But if this vector field is curl free, then yes, you'll recover the same. Or once again, I have like this comparison with like flow matching in my head. So like this that you'll recover the same vector field as in flow matching, and I think in diffusion models it's the same also, because like but there like it's might be even like with conditional score matching, because there it might be similar, because there I think the probability flow is just like this drift f plus like score, right? So so yeah, so then probably you should be able to recover the same vector fields, because yeah, so I think you can say that there is like a unique curl-free vector field guiding this distribution, and I think that pretty much answers your question, because then if you recover the vector field that satisfies the continuity equation, and it is curl-free, then it is unique, and you recover the same one.
Yeah, and in diffusion model, I mean, diffusion model is quite simple, because the vector field is f plus the score, as you say. If you can write f in terms of a gradient of potential, then it becomes the gradient of the potential plus the log probability, which is obviously curve-free. So you can show very easily that the actual vector field is curve-free for a diffusion model, if f is curve-free. And of course, you can also prove that that is the optimum of the loss. Of course, in the non-parametric clinic, but we're always talking about that. Okay, that's interesting. But so do you see potential if actually integrating this? Because again, we are using two different losses for getting the same objective, which suggests that maybe the best loss is neither of the two, right? There has to be some interpolating line.
In that regard, like once you have the because like in action matching we removed completely this degree of freedom that like we know how we define the forward process, we know how we define evolution, right? So we assume that we don't know anything because we want to use it for like natural sciences, right? And in generative modeling, that's an unnecessary restriction, right? Because you are the designer of your generative process. You are the designer of your forward and backward process. So you can select the right one, the one you like. And you have to assume the knowledge about the forward process. That's why I think for generative modeling, to generate images, like such things as like diffusion models and like these like conditional square matching and flow matching and all like other methods, they are better because they use these knowledge about the forward process, right?
Yeah, makes sense. Then. Although arguably that information is in the model that you use to sample. So arguably, if you train long, maybe there, in some sense, that information is there also for you. So maybe you just need to train for longer.
Yeah, that's true. That's true. So I think you can get very close in terms of like action matching to like these state-of-the-art models. I think if I would name like an application for image generation, that would be something like I think really something really kind of exotic when we don't have the forward process. For example, like for like compressors, right? Like if we have like this, if we instead of like adding just like normal noise, we compress our like image with some like via JPEG, for example, and then we can like just store less and less bits. And this process, we can also kind of make it like a continuous process, but then we don't know anything about what's happening to the compressor, and we want to like decompress. So maybe something like this would work for some niche applications where we want to like, I know, compress images or like yeah, or like do some like models where we like can adjust the quality on the fly kind of like easily. Yeah, so but just for image generation, I think it's just easier to use diffusion models or like flow matching.
Yeah, although maybe adding the time derivative information could regularize the model. I mean, they already work pretty well, but I could imagine a situation that could be
agree. That's actually a very interesting idea because I haven't experimented with the time parameterization at all. I just took like UNet, where like the take these like Fourier features, and maybe if you do something there, like if you take a different parameterization, maybe then it is adding something interesting to the model. Yeah, that's actually a good point.
Difficult to say, but at least it's interesting. I really like to see the connections between all these models are very interconnected. So I think it's, and I feel sometimes that there are different research communities. I don't, it's a bit of an opinion, but I don't like very much this flow matching literature because they use completely different language for describing something that is so similar to the diffusion model that I feel they could have used the same language. Like the loss is basically the same, and I just feel that we created two sub-communities of people that find difficult to read each other paper, but we are talking about the very same things.
Oh, I think that was like one of the purpose of like flow matching was to kind of like simplify the language and simplify the derivations for diffusion models. And I think that's like they were like they were like positioning it as like, yeah, this is like diffusion models for like practitioners who don't care about like what's going inside. And yeah, I know. Yeah, I know. For me, it is a bit different language, but feels kind of like the same. And but yeah, you can like also, I think you should. This is a paper that I think people don't usually know. It is like proposing the same as like flow matching, but on top of this, they propose also how to get like optimal transport, so they can get like potentially they can get the like one-step generation in the limits, like if they retrain the model and they show that like it actually works. So for example, if you go all the way down to CFAR10 results, oh, where is this? Yeah, it's, I think, yeah, it's here. So this, so 4.8 is their like result for FID for one-step generation. So like it's very impressive. It's very impressive. And the trick they use is that they do the following. So like once you do like linear interpolation, so you have like two marginals, right? So you have like these like purple marginals, marginal and red marginal. So once you do linear interpolation, you have like everything in between, right?
Yeah.
Then you learn the rectified flow, or it's the same as flow matching. Basically, you learn like an ODE that integrates like and goes from left to right, right? But then since the ODE is like has like a unique solution, right? You learn something like this. So this purple thing goes to the bottom like only.
Yeah.
So it rectifies the trajectories. Then you have these couplings. Once you have this coupling from your model, you can actually like you take, so like then you can define a different forward process. You take the purple dot, you integrate it according to ODE, you end up somewhere in this like red cloud, and then you linearly interpolate to this purple dot back, and it will give you like straight paths. So this is like linear interpolations now couplings, and this is like a boosting algorithm. So you learn, you have your like data, you learn like this rectified flow, then you redefine couplings between left and the right, you straighten the trajectories, you learn your model once again, and by doing this like iterative procedure, you can done it's like a very good model. Yeah.
Oh, that's very pretty.
Yeah. This one is very good.
Gianluigi, did you notice? You're very into this thing, right?
Yes, I also invited the speakers, but unfortunately didn't manage to set up a presentation yet with them. But I did notice this paper, yeah.
Very nice. Well, thank you very much. It was a very nice presentation and I think really fascinating work.
Thank you for inviting. It was a pleasure to talk about this. Thank you, guys.
Yeah, thanks. We had also very nice discussion, so it was very, very nice. Thank you so much. And then I will follow up with email also to ask for the resources that you mentioned.
Yeah, of course. Thank you, guys.
Perfect.
Bye.
Thanks,
Thank you very much.
Bye-bye.
Bye.
Bye.